Hello class. Today we're going to be starting chapter 9. I'll be assigning section 9.1 today. It will be due, our assigning today on Friday, April 17. It'll be due next Wednesday, April 22. Chapter 9 is a more in-depth look at solving second-degree equations. Let's make sure we understand what second-degree equations are about. Second-degree equations are where the largest degree of any term in the equation is 2. Hence, we call it second degree. The most common examples would be one like this, ax squared plus bx plus c, where a, b, and c are some numbers, but a cannot be 0. Otherwise, it would no longer be a second-degree equation. So an example would be maybe something like 3x squared plus 4x plus 5 equal to 0. Those are the most common types. Other examples would be if I had all y's in there, a y squared plus by plus c. Or another type that's not nearly as common is a xy, where I have an xy term. Notice the exponent of x is 1, exponent of y is 1. 1 plus 1, that degree of that term is 2. Hence, it would still be a second-degree equation. We've already done some of these, so this part next here should look familiar because we did it in the last chapter. If I had to solve one like that, if you remember, I'll start over here. We would take the square root of both sides. That gave me the absolute value of x. My pen is dying here. Wonderful time to do that. Equal to the square root of, or plus or minus, equal to 5. X then would be plus or minus 5. Pretty straightforward example. This one we needed complex numbers to solve. If you remember, we did that in last section. We took the square root of both sides. We got the absolute value of x to be, in this case, square root of 36, square root of a negative 1. That gave me x to be plus or minus 6i, if you recall. But again, we were able to solve it. Sometimes the radical wouldn't be a perfect square. We would take the square root of both sides, giving us the absolute value of x. This would be broken down into radical 4, radical 5. X then would have been plus or minus 2 radical 5. Again, all of these are examples of problems that we've already had. One more here to finish off this side. I would take the square root of both sides, giving me the absolute value of x. This would be radical 4, radical 7, radical negative 1. That would give me finally x to be plus or minus 2 radical 7i. Again, all of these are ones that we had in the last unit. One of the things I would like you to notice about this particular type of problem, we're going to do a few more, is that this bx term is missing. There's no 3x or 5x or negative 8x. There's no x term in any one of these. So when that x term is missing, we have an ax squared plus c. Here was 1x squared equal to a negative c, or whatever the number happened to be. We could just isolate the x squared and take the square root of both sides. These next three examples, very similar, just a little bit more challenging. Here I would have to subtract 8 from both sides, or I could say move the 8 over. If I move the 8 over, it would have been a negative, giving me a negative 24. Then I took the square root of both sides. we got the absolute value of x. This became radical 4, radical 6, radical -1. X then would be plus or minus 2 radical 6i. We had to isolate the x squared. Isolate the x squared, we got it by itself on one side. This looks much more intimidating, but it's really not much more, it's not much more difficult than this one. I first add the 11 to both sides. I'm trying to isolate this quantity squared, just like over here I tried to isolate the x squared. If I bring the 11 across, I get a 32. Then I would take the square root of both sides. Well, this square and the square root cancel each other. They cancel each other out, and you're left with an x plus 3/4. This technically would be a plus or minus. I could have the square root of 16 times 2. I would bring the 3/4 across. It would become a negative. Plus or minus 4 radical 2. Technically, there's two answers there. Negative 3/4 plus 4 radical 2. And x could be a negative 3/4 minus 4 radical 2. Again, we isolated the quantity squared. We took the square root of both sides, which canceled the square. We got it down to an x to the first, and then I just isolate the x's. This one a little bit easier. I already have it, this quantity squared, it's isolated, so I can immediately go to the square root of both sides. The square root and the squared cancel, so I get it down to a first degree. So I end up with 3 plus or minus 5. 3 plus 5 is 8, or 3 minus 5 is a negative 2. X could be either one of those quantities. I did this last one. I recognize it's a little easier than this one. At least it looks a lot easier. But I did that because I want to use this example on our next problem. Part of our lesson today is using the procedure of completing the square to solve second-degree equations. This procedure, not very common, but it's used an awful lot in higher mathematics. Completing the square is used, for example, when we're looking at parabolas, we're looking at hyperbolas, a lot of other conic sections. The last example we used was this one. We solved that one by taking the square root of both sides. Ignore the arrow for now, but we did all of this. We got those answers. Okay, we're looking at completing the square. If this original equation way up here, which I've copied right here, if it had been multiplied out, that means take this x minus 3 squared times itself. If I had multiplied that out, it would have been x minus 3 squared, which would be times another x minus 3. It would have been equal to 25. This would have been x squared. Minus 3x would have been minus 6x. Negative 3 times negative 3 would have been 9. And the equation could have looked something like that. Or I could have brought the 9 across and had it be equal to 16. If it were in one of these last two forms, it may not seem quite as easy for us as what this form was. Here I put it in this form right here. Okay? That would be if it were multiplied out. And I could have put the 16 on the left side. Different ways they might have written that. This particular problem, keep this in mind, remember this is important. This problem is the same as that problem. I just took that one and multiplied it out. These two are equivalent, okay? Completing the square, which we're looking at here first today, is a procedure we use to transform this last equation, the one right here, back into the first equation. I'm going to take this equation, transform it back into this one, so I can use this procedure. That's referred to as completing the square to solve. That's what we want to get here today. This is that same equation multiplied out. But now I'd like you to learn these next steps, okay? The first thing I'm going to do is I'm going to isolate the 2x squared of the x terms, which means I'm going to bring the 16 across, and I'm going to add two blanks. So I took this negative 16, moved it over, made it a positive, and I'm going to add two blanks. The reason I'm adding a blank here is I'm going to put a number in there, a well-chosen number, to make this left side into x minus 3 squared. I want this whole left side to be a quantity squared. I have to choose the correct number. The reason I need to choose that correct number is it has to be a perfect square, like this, x minus 3 times x minus 3. So here's how I choose this perfect number. I take half of the x term and square it. I'm going to say that again. Half of the x term and square it. So what is half of a negative 6? Half of a negative 6 is a negative 3. Squared is 9. I need to add a 9 into both sides. I added that half of the negative 6 squared to both sides. That basically made it into a 9. You would need to figure out that number. Again, it's half of the x coefficient squared. Then this side is a perfect square. It's the same thing as x minus 3 squared. These two I just added together. And now I follow the same old procedure that we used in last chapter. I take the square root of both sides, get x minus 3. Remember this square root and the squared cancel. And I get plus or minus 5. Bring that negative 3 over. That negative 3 gets brought over. It's a positive. 3 plus 5 is 8. 3 minus 5 is a negative 2. But completing the square is this process right here. Again, don't be afraid to take a picture of that. That's the procedure of completing the square. We're going to do that procedure here multiple times. You will be expected to be able to do that on your assignment as well as on the next test. So here we go with a bunch of examples. Okay. The first thing I'm going to do is isolate the two x terms, which means I'm going to bring the 45 across. If I bring that 45 over, it'll become a negative. It's the same thing as subtracting 45 from both sides. But then I'm going to put a blank in I'm going to add the same number to both sides. Remember, it has to be the same because the same number doesn't change the equation. How do I find that number? Well, I take half of the x coefficient. The x coefficient is 12. Half of that is 6. So I take 12 divided by 2, which gives me 6, and I take the 6 and I square it. That's the number then, 36, that I need to put in both blanks. That gives me then a negative 9 over here. Well, then this side becomes a perfect square. It's x plus 6 and x plus 6. This side happens to be a negative number. I can square both sides. The squared and the square root cancel. I get x plus 6. This is going to be plus or minus 3i. When you simplify it, I get a negative 6 plus or minus 3i. That's really two answers. It's a negative 6 plus 3i, and x could be a negative 6 minus 3i. Those are my two answers. Right up here, that was the process of completing the square. I'll go a little faster this time. I need to get the x terms on the left side. I bring that negative 6 over, it becomes a positive 6x. I'm going to put a blank in for what I need to add to both sides. Half of this number is 3, squared is a 9, so I'm adding a 9. Make sure that you understand where I got the 9 from. I took this 6, cut it in half to make it 3, and I squared it to give me 9. That makes this factorable into a perfect square. This side is 14. We take the square root of both sides. I get x plus 3, plus or minus in this case. I'm sorry, that should be a 14. Plus or minus the square root of 14. My answer is negative 3 plus or minus radical 14. That one was a little bit easier. This next one is a little bit more challenging. Couple reasons. You see that I have a fraction, but more important than that even is this number is not an even number. So far I've had even numbers. When it was an even number, when I cut it in half, I had a nice integer. Here was an even number. When I cut it in half, I had a nice integer. When I have an odd number and I cut it in half, it's not going to be so nice. So I start off and I need to take this negative 5, cut it in half, or that means divide it by 2. It's not a nice integer. But then I also need to square it. If I take that 5, cut it in half, divide it by 2, and square it, I get 25 over 4. That's the number that I need to put in these blanks. 25 over 4. Super important that you can get that 25 over 4. That's how it was done. Well, this might not be so obvious now what the factors are. But let's go back here once. And how did I get this x plus 3? I took the 9 and took its square root. How did I get the x plus 6 here? I took this 36 and took its square root. So what am I going to put in here? My sign will be positive, or excuse me, my sign is negative because this is a negative number. But remember, square root of 9 gave me 3, square root of 36 gave me 6. I need to take the square root of 25/4, which is 5/2. Square root of 25 is 5, square root of 4 is 2. This side, I just need to add those fractions together. Then I take the square root of both sides. This, by the way, is actually the number 9. Again, the square root and the squared cancel, and I get x minus 5/2 plus or minus 3. That gives me a negative 5/2 plus 3 and a negative 5/2 minus 3. Plus 3 is like 6/2, so this would become 1/2. Minus 3 is a negative 6/2, that would be a negative 11/2. Those are my two solutions. I would like you to try these 3 once on your own now. I'm going to give you a head start, but then I'm going to try all 3 of them after you. And those should be your 3 answers if I didn't make any careless errors in this process. To get this factor, this sign comes straight down. We take the square root of the term that I added. To get plus 4, this plus came straight down, took the square root of this number that I added. So the square root of 9/4 was 3/2. This procedure can get a little more challenging, as we're going to look at here now, okay? When way that it gets a little more challenging is if our leading coefficient does not equal 1. What do I mean by that? Well, on this previous page, my leading coefficient, I had a 1x squared there, I had a 1x squared, I had a 1x squared, 1x squared. All of those leading coefficients were 1. What happens if it's not equal to 1? For example, here it's 3. Well, when it's not equal to 1, we have to factor that number out to make it 1. In other words, because it was a 3 instead of a 1, I factor the 3 out. That leaves me 1x squared right there. But because I took the 3 out of the x squared term, I also need to take the 3 out of the 6x term. If I factor a 3 out, I'm left with a 2x. Notice 3 times 2x would give me the 6x. Then I left a blank to add. Now, this next step is a little trickier. Remember, I take half of the number in front of the x. That number is 2. If I take that in half, it means I cut it in half, and then I square it. Well, that happens to be 1 squared, which means I put a 1 in there. But be really, really careful here now. When I added a 1 to this left side of the equation, the 1, notice, gets multiplied times the 3 eventually. So really, I've added a 3 to the left side. So I need to add a 3 to the right side. It doesn't look like these two numbers are the same that I'm adding to both sides, but because this 1 is taken times 3, I'm really adding 3 to both sides. That's a tricky spot. So I just put it in red here to make it just a little more obvious. Now notice this in parentheses is a perfect square. That x squared plus 2x plus 1 in parentheses is a perfect square. It factors into x plus 1, x plus 1. So it really is x plus 1 squared. That's why we call it completing the square. I added this 1 to complete it, to make it into a perfect square. So that means this left side can be factored, and it looks something like that. Notice the challenge that we had here. The leading coefficient was not 1. We factored it out. We completed the square in the parentheses, recognizing that whatever number I had to take it times 3 to make it equivalent on the other side. Now I'm going to try and isolate the quantity squared. So I would divide both sides by 3. If I divided the left side by 3, it cancels. Divided 48 by 3, I get 16. Now it's same old, same old. I take the square root of both sides, get x plus 1 plus or minus 4, bring the 1 across, negative 1 plus 4, negative 1 minus 4, and I get my answer. Make sure you don't miss what was more challenging about this one. It's the fact that my leading coefficient was not 1. Okay, the leading coefficient is now 1. I would like you to try this one. I'm going to do it shortly, but I'll give you a head start. Don't be afraid to pause it here and copy these two. I've given you two examples here. Notice this time I put a 9 in there and a negative 36 out here. Why did I do that? When I put the 9 in, it's really 9 times a negative 4. And that's a negative 36, so that's why I had to add negative 36 to the right side. Make sure that you could do both of these, excuse me, examples. I'm going to switch gears here now and look at something I think many of you will find much easier and also much more familiar. Keep in mind we're solving second-degree equations. That procedure we just found, completing the square, will solve any second-degree equation in the form of ax squared plus bx plus c equal to 0. Occasionally, this doesn't always work, but occasionally there's another method that works for some second-degree equations. This other method we refer to as factoring, but it's super important when we solve by factoring that you recognize and understand here a very important concept. Here's the concept. If I happen to have some parentheses times another parentheses and it equals 0, well, the only way I can multiply two things together and get 0 is one of these things, or maybe both, but for sure one of them must be equal to 0. Can't emphasize how important that is to understand that. If I have two things being multiplied and their product is 0, it means at least one of them has to be 0, maybe both. In other words, what do I know about this A or this C? Here's what I know. Either that A has to be 0 or that C has to be 0. What you see in red here is a basic fundamental building block of solving by factoring. We must understand that. Now, one other thing, a detail, notice the original, it's up here, must be equal to 0. The reason I say that is, let's go back here. Let's just say it's not equal to 0. Let's say it's 12 instead of the 0. Well, if it's 12, we're not sure what A and C have to be. A could be 1, C could be 12. A could be a negative 1, C could be a negative 12. A could be 2, C could be 6. A could be 6, C could be 2. A could be 3, C could be 4. I have a whole bunch of possibilities there. And I haven't even begun to look at fractional possibilities. Technically, infinite amount of them. However, when it's equal to 0, then we're sure about one of these two things. That is super, super important, okay? Important concept. I'll come back to that off and on here in the next little while. This is a procedure I'm guessing many of you have seen before. So I'm looking at a real simple example here, x squared plus 6x plus 5 equal to 0. Notice I have it equal to 0. I can factor the left side. I need two factors of 5 that add up to be 6. Those are my factors. Again, notice it's equal to 0. I'm reminding you this x plus 5 is like the A. The x plus 1 is like the C. What do I know about those? You remember I know that either this A is 0, that means x plus 5 is 0, or this C is 0, that would mean x plus 1 is 0. That's how I get from this equation down to the next one. Either the first one has to be 0, it's like saying the A has to be 0, or this second one has to be 0, it's like saying C has to be 0. Then I solve both of these for x. I bring the 5 over and I get a negative. I bring the 1 over and I get a negative 1. If I take either one of these answers, put them back in here, it will make the equation true. The original, though, must be equal to 0. That original there has to be equal to 0 so that I can use this principle. So now, solving these by factoring, I need to get it equal to 0. Bring the 12 across. It's a negative 12. I get it equal to 0. Here's where your factoring skills come into play. Need an x and an x. My signs have to produce a negative 12, so I need one positive, I need one negative. Because they're opposite signs, these factors of 12 have to have a difference of 4. Those factors are 2 and 6. The 6 needs to be negative. Put that with the negative. The 2 would be with the positive. You can multiply it out. You'll check it does check out. But again, remembering now this principle in red, 2 parentheses times each other to be 0 means the first one is 0 or the second one is 0. So that means this x plus 2 equals 0, or the second one, x minus 6, equals 0. That means the x is a negative 2 or the x is 6. Both those numbers, if you put them back in here, will both make a true equation. This next example, I'm going to move the 8x over. I'm going to move the 33 over. It will become a negative. I did that again so that it equals 0. So that it equals 0. That's crucial. Otherwise, factoring isn't going to help me. I need 2 factors of 33. One has got to be positive. One has got to be negative. They need a difference of 8. They would be 3 and 11. You can check it out, but that makes this x plus 11 equal to 0, or the x minus 3 must equal 0, which means the x equals a negative 11, or the x equals 3. This one is not going to be as easy to factor because its leading coefficient is not 3. But I still need to first get everything equal to 0. So I bring the negative 2 over, it becomes a positive 2. The factors are a little bit more challenging to get. This may take you a little more time. I need to have a 3x and a 1x. My signs are all positive. I need the factors of 2, which have to be 1 and 2, but I got to be careful where I put them, because this number gets taken times 3, this number gets taken times 1, and they need to add up to be 5. That means the 2 must go here, and the 1 must go there. If I switch them, I won't get the 5x. Now again, I have parentheses times parentheses equal to 0. It means either the first one must be 0, or the second one, x plus 1, must be 0. Then I bring the 2 over and divide by 3 now. When I bring the 2 over, it's negative. Divide by 3, I get a fraction. This one, I just bring the 1 over. And those are my 2 answers. Notice when that coefficient is not 1, we have to be more careful with the factors, and we likely get a fractional number there. This is another one that is tricky for a lot of students. You'll notice there's no number here. For example, here I had a number negative 12. Here I had a number negative 33. Here I had a number 2. there isn't any here. When that happens, it's actually a little bit easier, but a lot of students don't get that. I'm going to factor out whatever I can from both of those. If there's no number there, I can always factor out an x. But in this case, I can factor out a 5x. And I would be left with that. Two things are being multiplied to get 0. Two things are being multiplied to get 0. Either the first thing is 0 or the second thing is 0. So either this 5x equals 0 or the x minus 4 must equal 0. Dividing both sides by 5, I get x to be 0 there. 0 over 5 is 0. I bring the 4 across, and I get a 4. So those are my two answers. Unfortunately, take a look at the last one. It's already equal to 0. I have a number there. But if I try and factor, the only factors of 1 are 1 and 1, and they will not add up to be 2. It's not factorable. I cannot use factoring to solve it. I would have to complete the square. That would have been the procedure we learned in the first half here. All of that said, to finish up our lesson today, I'd like you to try these 3. I'm going to do them after you get a head start. That concludes our lesson for today. Again, as I mentioned earlier, I'm assigning this particular section 9.1 today, and I believe I gave you the dates for that. I'm assigning it today, April 17. It's due next Wednesday, April 22. Have a good rest of your day.